Hi friends, so today we are going to start Fortran tutorial lecture 2, and today I'm going to discuss various simple programs. We are going to look at the different math functions I outlined in the previous lecture, and also we are going to look at some ways how we can deal with complex numbers and so on. I am Dr. Ganguly. So let us begin with some expressions, mathematical expressions or formulas, and try to translate them into Fortran. So of course, as I mentioned in my previous lecture, Fortran essentially means formula translation. So the for comes from formula, the tran comes from translation. So again, let us take an expression like this, which is essentially composed of integers. Now remember that I, j, k, l, m, n are classified as the integers in Fortran. So I can write this particular expression as n term is this expression here, that is I plus j minus k into l plus m to the power 3 divided by n, and then this entire expression I can print it out and I'm calling it n term because of course this is something which is composed of the integers and I want the output to be an integer also here. So I copied and pasted this particular program snippet here in one compiler, which is an online compiler I have found, and then I put in certain input values. So essentially I, j, k, l, m, n are 1, 2, 3, 4, 4, 2, and I got the output to be 23. And I checked it out here. So if we check it out here, we plug in the various values, you also get 23 here. So this is a simple program about how integer arithmetic takes place. Now, of course, you can see that as far as Fortran is concerned, you do not need to define the variables if you are using the implicit definitions which are out there. Of course, some people used to object to this, and there were languages like Pascal and later some more languages where it was considered that it's not a good idea to not define variables. But if you take Python today, it essentially has the same kind of mindset. You don't need to define variables to work. So that's something which has happened, that we have come back to the same philosophy after many decades. Now let's start getting into some real calculations or real number calculations. So again, let us take this particular expression, which is absolute value of sine A plus log B cos A minus e to the power B. Now here, of course, log B, when we write it as ln, this is the natural log. So what I have written here is a basic program to calculate this expression, or rather I should say a simple program to calculate this expression. And I have divided this into two parts, a numerator part and a denominator part. So the numerator part is simply abs sine A plus A log B. Remember, A log is the natural log, A log 10 is the log 10. And then the denominator is cos A minus e to the power B. And I get term as A num by den. Again, remember that I converted this num here to A num just to make sure that these are all real numbers here. So again, if you are not starting with I, j, k, l, m, n, then you are implicitly assumed to be real in Fortran. So I pasted this code into the one compiler and I put in the values of -1 and 2 for A and B, and I obtained the output as minus 0.224. And again, if you do the calculation here, you can do it on your calculator, you can even do it on your phone. What I again get is the same value here. So this is something which tells you that Fortran has a lot of inbuilt features out here. For example, the sine, the cos, the exponential, the log, and so on. You do not need to add any numpy or scipy in Fortran. Now let's take this particular expression, which is the fifth root of a plus b to the power minus 3 divided by sine ha minus cos hb. These are the hyperbolic sine and cosine respectively. I again write a program here. So I write the numerator as a to the power float 1 by 5. Now I could have written this as simply 1.0 by 5.0 because I do not want to divide 1 by 5 in integer arithmetic, I want the compiler to know that these two are to be treated as real numbers. And of course, a simple way is to write 1.0 by 5.0. But I want to bring out this float function. What it does is that it takes the int value and converts it into floating point. And here, of course, I have b to the power -3. I have denominator is sin ha minus cos hb. Now here I have not bothered to write minus 3.0. You could do it if you want, because b itself is a real number. So this entire thing is going to get converted into real numbers. So I can get the value of this term or expression as a num by den, and so then I can print this term out. So what I do is I put this code into the compiler, and then I run it for values of a and b as 2 and 3, and I get this as the output minus 0.184097. And of course, if I do this by hand calculation, you can do it on a calculator. I get the same value here. Now, it's sometimes nice idea to check some basic things by hand calculator for at least 1 point. Sometime we can then later put this entire thing in some kind of do loop, and then we can get thousands of values of that particular function. But it's a good idea to sometime check these things because you may make some typing mistakes. Now let us look at something which is actually based on integers, and here I'm going to use two functions. I'm trying to create this particular problem to illustrate these two functions, and these are nint and int. So what nint does, it's going to take some real number and it's going to get the nearest int value, and int is going to truncate it to the int value. So here I have this expression here, absolute value of I to the power n int a minus j to the power int b, and I want remainder of I by j. So whatever remains, if I divide I by j, I want to have that in the denominator here. So let's write a simple code for this. So first I read a, b, I and j. Of course, a and b are real here, I and j are int. I can write the numerator as I abs to the power I abs I, which is this value here, to the power n int a, which is this value here, minus j to the power int b. And after I have done this, this is of course something which I want to do in integer math. So I have kept all these numbers as int numbers. I writeiden as mod I by j. Now this is going to give me the remainder of I divided by j. Some compilers also use I mod, but mod seems to be working for this particular compiler. Then I write I term is num by iden. Remember that all the values here are starting with I, j, k, l, m, n. So I am trying to make sure that I am using int calculations because I have converted the floats here to int also. So then I print out the numerator, the denominator, and the value of this particular term here, which is this expression in blue. Let's now put this in the compiler, and once I put it in the compiler, I give it some values. I give a, b, I, and j as 3.8, 3.8, minus 40, and 17. And I have printed some of these values out to show you how these different functions work. So for example, what n int a does, it will take 3.8 and it gives the value 4. So this is essentially the nearest int value. And what int b does is that it takes 3.8 and it truncates it to 3. So essentially these two have different sort of actions here. And of course, what the remainder will do is it will divide minus 40 by 17 and gives us the remainder, which is -6 in this case. Remember, 17 into 2 is 34. So if I were to do this calculation by hand, I can do all these steps and I'll end up with 425,847. That's the same value I get here. Of course, remember this division is taking place as an int division. So this is what the computer will give you. Of course, if you do it in your calculator, you will get something like this, because then the calculator is treating this as a floating point division. So this is something you need to keep in mind when you are dealing with int and real variables. Now let us take one more expression. So what I'm trying to do is I'm trying to give all the expressions which I discussed in the previous lecture. And so we remember that there were also functions for arc sine A, arc cos B, and so on. So here I'm going to use these functions here. So here we have arc sine A, we have arc cos, we have arc tan, we also have log 10. So there is a function for log to the base 10 also. And now I write this code here that I read A and B, I calculate the numerator as A sine A plus A cos B, that's the numerator here. We have built-in functions in Fortran. We write the denominator as A tan A plus cos 2.0 into A log 10 B, and then I simply calculate term is A num by 10 and I print this value of the term here. So I copied and pasted this into this online compiler, and then I gave the values of A and B as zero point 0.5 and zero point 0.7, and I got this particular value here 0.9314. So that's the value here also. So this again shows you the power of Fortran in terms of the different functions which are built into the Fortran programming language. Now, of course, remember here when you are taking the inverse of sine and cos, these values have to be between -1 and 1, because the sine and cosine of functions are of course bounded between these two values. If you give some random value like 4 or 10 here, this is going to give you NaN, or basically it's going to tell you that this program is not working. Now let us take a situation where we are combining some real and int values. So I have e to the power j into a minus j sine a by root j log a, and here j is int and a is real. So let's write a code for that. So you get read ja, then what I do is I convert j to floating point, because I don't want to do all these multiplications by themselves. It may happen very well, but what may happen sometime is that you may end up in trouble trying to take square roots and all of int values and so on. So let's convert it to floating point, and that's where this float function comes in handy. So I say aj is float j, and of course I have also made it very clear that aj is a real number by starting with a. Then I get the numerator as as exponential aj into a, that is this j into a minus aj into sine a, and denominator as square root of aj into a log a, and then I get the term as numerator divided by denominator, and I print this term. Now what I have done here, I have put it in the compiler here and compiled it, and I run this code here with values of 3 and 2 for j and a respectively, and I get the output to be 333.7599, which is what you see here. And I also printed out the numerator and denominator in this case to solve this problem. So this is another thing, of course, a good programming practice is that you can print out sometime the intermediate variables if you are interested in seeing how the code is working out. Now let's return to the quadratic equation which I had looked at in the last class, and we are going to address the issues of possibility of getting complex roots, because this b square minus 4ac may actually end up being negative. So of course you know that the quadratic equation ax square plus bx plus c is 0, has roots x is minus b plus minus root b square minus 4ac by 2a. This is the well-known quadratic formula. So again, our formula translation is here. This is the formula here, and we had written a simple code here. Now I have dispensed with trying to define all these things as real, because if we are not doing it in Python, why do we need to do it in Fortran if we don't want to? So if you of course want to, you can do it, but we are just writing the smallest piece of code possible to get the job done. So let's read ABC. We get the particular value inside the square root, then get x1, x2, and print x1 and x2. Now this of course is a problem I can very easily solve. So I have put this particular piece of code here, and I compile it and I run it with 141, that is A B C R 141, and I have got the solutions here as negative 0.2679 and negative 3.73205, which you can actually verify by hand calculation using a calculator. So clearly there were two real roots, both negative numbers, and we have got that because the case A is 1, B is 4 and C is 1 gives you nice real roots. But now let us say we take the case where A, B and C are 1. So actually here I should have put a 1 here, but what I have done is I have calculated all this with A, B, C 1, and so I end up with the solution NaN, which essentially means that the computer is not able to resolve this particular issue because it doesn't like the fact that the square root of a negative number is coming in. So that's something you have to keep in mind, is that when you get NaN, that essentially means not a number. It does not mean the naan which you can get in the Indian restaurant. But there is a good way to solve this particular problem if you know about complex numbers. So what you can think of is any complex number a plus bi can be written in Fortran as a comma b, or as a pair. You can think of it as like a coordinate also. So if we go back to this equation, again we put a is 1, b is 1 and c is 1. We solve it, we get this complex conjugate roots, and so the roots are x is minus 5 plus minus 0.866i. Now here all I did is in the code I declared a, b, c term x1, x2, which are all the variables used in the code, as complex numbers. So I put this particular statement here, and then what Fortran was able to do, it essentially uses complex math and it gets the root. So I have to give the input values of a, b, c as 1 0 1 0 1 0. So of course, since the values are a is 1, b is 1, c is 1, the real parts are 1 and the imaginary parts are 0. So I get the solution here. So the negative zero point 0.5 is the real part, and of course the other two parts are the imaginary part. There is one part which is 0.866 and the other part which is negative 0.866. So you can clearly see that Fortran is very powerful in terms of the fact that it can not only deal with real numbers but also deal with complex numbers. And you may have to sometime play around because some of these functions are different depending on the compiler you are using. So do keep that in mind, and you can easily verify any of these things by searching in Google for the particular thing. For example, if you were to search complex numbers in Fortran, you will get all the information you need to do that. Now there was one more homework problem I told you, a very simple problem which is very often presented in textbooks, and that is you want to convert centigrade to Fahrenheit or Fahrenheit to centigrade. So most people try to convert Fahrenheit to centigrade. So let's try to convert centigrade to Fahrenheit here. So essentially the formula is F is 9 by 5C plus 32. So you can check that this satisfies the end conditions, that is at C is 100, F is 212, and at C is 0, F is 32. So very simple program is simply to read the value in centigrade, calculate the value in Fahrenheit and print it. I don't have to worry about F and C because I know that these are both real numbers. They are not I, J, K, L, M, N. So I just copied the code here and I ran it with 40 degrees centigrade as the input, and I get the output to be 104 Fahrenheit, which is the output here. So this is generally a temperature which is considered hot by most people. So today's lecture you learned a lot about the different functions which are out there in Fortran, which you can use to do many problems, and as a homework problem you can try to do this, that try to solve this particular quadratic equation px square plus qx plus r equal to 0, where p, q, r are actually defined using these particular formulas here. Now you can check out this whole thing with some value. I have just cooked up some value like a is zero point 0.5, b is zero point 0.3, and you may use some different values also. In many cases you may land up with complex numbers if you are choosing any random values. So in those cases you can try to see that you can use the complex number aspects of Fortran also. Now you can try to use a different type of programming language also to see how it comes about. For example, most of you may be knowing some language, typically Python, but also if you know a different language, maybe Java, C++, Rust, and Go, try to write a code in that language to do this problem, and it will probably give an interesting experience to you. Now, one thing I didn't mention today is that something which most of you know is that as far as the angles are concerned here, for example, whatever is A here, the a values here and so on. All these things are going on in radians. So if you are given any particular angle in degrees, then of course you have to convert that to radians to solve any problem. So that was the tutorial 2 for today. In the next tutorial, I'm going to look at the control flow statement, that is the if then else statement in Fortran. And also maybe we will talk about the do loops, for example, the do continue, or sometimes people also use the do and end do. So those things will now start bringing the Fortran to the level of actual scientific computing, because in scientific computing the main things which are required are, one is the do loop and one is the if then else statement. And of course historically also you will see that though Fortran was invented a long time ago in 1957, it did have some of these very powerful constructs which are then present in all the remaining Fortran remaining programming languages also. So I'll end this video now and I will see you in a new video sometime soon, and I'm leaving some videos on the end screen which you can look at to continue your research and education journey.